Hello, we're back with another Can We Do That video, and today we're taking a look at sequences, because of course we can define a sequence using its nth term, which is then useful if you're trying to then generate the terms in the sequence. We can even then take it one step further by adding the terms in a sequence to form what we call a series. And we've even got some useful notation to show this, which is of course the capital sigma notation. And then we even have formulas that allow us to quickly work out the value for certain series, which is super useful if you've got a series with a lot of terms where you don't want to be calculating it manually. But what happens if instead of adding the terms in the sequence, you want to multiply those terms together? So therefore today we're asking the question, products of terms in sequences, can we do that? But before we continue on any further, I must warn you. Yes, as usual with these videos, they're just for fun. We don't need to know this stuff for an exam, but at the same time, our curiosity probably still wants to be satisfied. So, therefore, let's start off with some simple ideas. If we've got a sequence with the nth term of 2n, and we're going from the first term to the fifth term, that of course would be the first 5 terms of that sequence. And we could then decide that we want to find the product of those 5 terms. Now, for this particular product, it wasn't too much effort to write it out manually, but if I was including more terms than this, I'd very quickly get bored of having to write them all out. So wouldn't it be super useful if we had a nice bit of notation that we could use to more efficiently notate this stuff down, just like we do for series? Well, good news, we do, because all we got to do is use the Greek capital letter of pi in this sort of format. Yes, I do mean pi, which is of course something we're usually used to seeing when it comes to circles and trigonometry, representing the number 3.14159265535 truncated to 10 decimal places, but this time we're using the capital letter version of it as opposed to the lowercase version, which is what you're used to normally seeing. And the good news is that this notation is fairly intuitive if you've already dealt with sigma notation before, because the number that's at the bottom of the notation is indicating what position in the sequence you're starting at, the number that's on the top indicates what position in the sequence you're finishing at, and therefore in this case that's telling us we're starting at the first term of the sequence, going all the way through to the fifth term in the sequence, and then what's written after the capital Pi notation is indicating the nth term of the sequence you're doing the product of the terms for. Nice, so that's pretty useful, but it also leads me to explain partly why I chose to do this topic today, because ultimately if you understand sigma notation, understanding this stuff is not really any more difficult. Yet at the same time, this is a topic that receives a lot less love when it comes to the design of exams and syllabuses across the world. So I thought I'd correct that and give ourselves a time to explore this stuff today. It gets even more mysterious though when you start looking at calculating these things, because if you turn to your calculator for help, although an increasing number of modern scientific calculators now including a mode that allows you to calculate series by typing the series in using capital sigma notation, a quick glance through the calculators that I own seems to suggest there isn't really equivalent modes for calculating products, at least not widespread. Which causes a problem, because it means we're going to have to manually calculate these things, and as most people probably don't have the time or patience to manually type out 2 times 4 times 6 times 8, etc, etc, what we're going to want is some formulas to allow us to do this stuff. So let's take a trip back to something even more simple by looking at a sequence with the nth term of r. I mean, I'm using the term nth term there, which is technically not correct, because now the letters R, I should be saying rth term, but as that's a pain in the butt to say, for the purposes of this video, I'm going to continue referring to it as an nth term, even though the letter R is what I'll be using throughout the rest of the video. Anyway, we've got this sequence with the nth term of r, and therefore it means it's the very simple sequence of 1, 2, 3, 4, 5, etc, etc. So if we're doing the product from the first term to the fourth term, this is what we're trying to calculate. And you see, when you look at this, you might start to go, wait a minute, haven't we done this sort of calculation before? If you're calculating the product of all the positive integers from 1 up until a fixed endpoint, then isn't that just factorials? And you'd be right. it is. This, of course, would just be the calculation for factorial, and therefore that would come to 24, and therefore in general we can say that this formula is true, which is great, because it now means we've got a starting point to be able to actually start calculating some products. But that's assuming we're always starting at the first term. Yet, what happens if we're not? What happens if, for instance, we want to start at the fourth term, and then go, in this case, to the seventh term? Well, of course, in that case, we'd be calculating 4 times 5 times 6 times 7, but that isn't going to be factorials anymore, because factorials have to start directly at 1. But we can still use factorials to help us. For instance, if I do calculate 7 factorial, that is finding 1 multiplied by all the integers all the way up until 7, and that does include all the numbers we wanted to multiply together in this product. However, it is also including some extra terms we don't want, the 1, the 2, and the 3. So to deal with the fact that we don't want them, we could divide by them again, because then that would be meaning we're finding only 4 times 5 times 6 times 7. But good news, 1 times 2 times 3 is also just another product that we already know how to calculate using factorials. It's just going to be, therefore, the product from 1 to 7, 7 factorial, divided by the product from 1 to 3, which is 3 factorial. And therefore, if you calculate that, that's going to come to 840. Nice. Those of you who are eagle-eyed also might recognize this structure of a factorial divided by another factorial from other areas of maths too. This is related secretly to what NPR does as a function. So actually, therefore, in general, we can say if you're doing a product that starts at r equals a and finishes at b, then therefore this is the formula for it in terms of factorials, or alternatively, in terms of NPR, it would be this. However, because I'm aware that not all of you would be all that familiar with using NPR, and because it could be argued that it isn't actually really saving on any notation here, I'm not going to be using NPR for the rest of this video. Anyhow, let's step it up a notch and go back to what we were trying to work out before. What happens if we're working out the product of this sequence? Well, we've now got that constant of 2 out the front being multiplied by the r, so how does that affect things? To understand how we might approach this, let's take a trip back to sigma notation and remind ourselves that if we've got, for instance, an nth term like r plus 3, then that's actually very easy to work out the series for, because the sigma notation can be applied individually to the two terms that are separated by the plus in this case, but the same would be true if they're separated by a minus sign as well. This works and makes sense that it works because ultimately sigma notation is to do with adding, so of course it interacts nicely with other additions and subtractions. So therefore, if we're now looking at a product of something that's of the form something times by something else, then yes, we can apply that product to those two things individually and then multiply afterwards, because ultimately product is just to do with multiplying, and therefore it's going to interact nicely with other multiplying actions. This works because multiplication has what we call the commutative property, which is basically a posh way of saying it doesn't matter what order you multiply two numbers in, which allows us to reorder the terms in this product so that we're doing all the 2's multiplied together first, followed by the product caused by the r. Therefore, that makes it very easy to calculate this product, because the product of r from r equals 1 to 5 is of course what we've already been dealing with. It's just going to be 5 factorial. And then the product of 2 from r equals 1 to 5 is talking about the product of a sequence with an nth term of 2. And because we're doing from the first term to the fifth term, that means we've got 5 2's all being multiplied together, and therefore that just means we can use indices, just simply write that as 2 to the power 5. So therefore, overall, this product comes to 2 to the power 5 times by 5 factorial, which gets us, in this case, 3,840. So that's great. We now have a way of being able to calculate a bunch of products of this sort of style. The next thing we might try to play about with is what happens if we've got an nth term with an added constant involved. Something that was so easy to do with series, yet when we get to working out the products of these things, that's where things get really weird. Because, you see, there are some products of this type where there is going to be a really nice formula still in order for us to be able to calculate it. Yet, some other sequences with seemingly similar nth terms don't result in something that's easy to calculate with a formula. So, what's going on here? Well, part of this discrepancy is just down to the fact that there is no nice way to be able to split up things separated by a plus or a minus when it comes to finding a product. So that means if we're trying to find the product of the second of those two sequences we showed before, 5r plus 7 from the first term to the sixth term, if you were to fully write it out manually, this is what it would look like. And the problem is with those brackets, although you could multiply them together and you'd find some things pair up in a nice pattern, some of the other combinations involved when multiplying everything by everything in those brackets will lead to some things that there is no nice formula to just instantly calculate. So therefore, that's a bit annoying. So how come there are any of these types of sequences that we can find a nice formula for? Well, it's all about the relationship between the coefficient of r and the constant that's been added on. What you're looking for is for that constant to be a multiple of the coefficient of r. In this case, you can see that's happening because 6 is a multiple of 3. That's important because it allows us to apply a little trick that we otherwise can't normally do. What we can do in this case is we can factorize that coefficient of r out of both terms. So that leads us to 3 lots of r plus 2, and that's really useful because it allows us to do a substitution. We could say let u equal r plus 2, and therefore what we can do is we can rewrite this product so it's in terms of u rather than r. That means its nth term will now be, instead of 3 lots of r plus 2, it'll now be just 3u. And we're starting at r equals 1 going to r equals 7, but r equals 1 is equivalent to u equals 3 by our substitution, and also r equals 7 would be equivalent to u equals 7 plus 2, so u equals 9. So therefore this is the product we're now calculating. That's wonderful news, because we know how to calculate those products now, so let's go ahead and do it. It's just going to be the product from the first term to the ninth term of 3u divided by the product from the first term to the second term of 3u, because that will eliminate those extra terms we don't want when doing that product on the top of the fraction. And therefore that is just simply going to be 3 to the power of 9 times by 9 factorial, all divided by 3 squared times 2 factorial, again using some of the skills we said earlier about splitting up that 3 from the u and calculate them as two separate products. Nice, that will become 396,809,280. This does lead to a bit of a bizarre side effect though. Because we're doing these substitutions and therefore altering the number that's at the top and the bottom of the capital Pi notation, that can lead to some very strange results. Let's say for instance we've got the product of the sequence 4r minus 28 from r equals 1 to r equals 6. Again, we can do the trick of factorizing the 4 out of both terms because 28 is a multiple of 4. We can then do a substitution. In this case, I'm going to let u equal r minus 7, and that means our nth term will become 4u, but then we're going to have u equals minus 6 and u equals minus 1 on the bottom and top respectively. And then for the product that's on the bottom, again, we can factorize the coefficient of r out of both terms. So we choose a substitution. This time I'm going to say let v equal r minus 3. And therefore the product's going to become the product of 5v, but from minus 2 to 2 when we also substitute the values of r using the substitution. The weird thing about both of these is it means we now have negative numbers in this notation, which is something that just feels wrong to have, and it's something we generally didn't ever have to deal with when it came to series, partly because this trick of doing the substitution was practically never one we ever had to do. This is also a bit weird because it might tempt you to start trying to question whether we can calculate negative factorials, but that would all get a bit messy and you might end up not calculating what you're actually trying to find here. So let's look at what's going on manually to fully understand what it is we're trying to find. For instance, if you're trying to do the product of r from r equals minus n to r equals minus 1, where n is any positive integer, then therefore what you're finding is the product of a sequence that looks like this. This unfortunately is not something you can just calculate using the traditional factorial function, and therefore we're going to have to apply a little bit of a trick to help us calculate what this is going to become. Conveniently, all of these numbers have a factor of -1, so you could factor -1 out of every single number in this sequence. But because there's n numbers in the sequence, we're going to have to factor out -1 n times, so therefore we're going to have a factor of -1 to the power of n out the front. Then we've got the 1 times 2 times 3, etc., onto multiplying by n afterwards. But wait a minute, that is now just a factorial, so it's -1 to the power of n times by n factorial. And the second of those weird scenarios we dealt with had a situation where we had a negative number on the bottom of the capital Pi notation and a positive number on the top. If you're applying that to the sequence with the nth term of r, that means we're dealing with a sequence that looks something like this. We're starting at -a, working our way through all the negative numbers until we eventually reach the positive numbers, and then working our way up all the way until we get to b. The thing about this product though is it's always going to include 0 if r is spanning from a negative number to a positive number. And you see, the thing is, it ultimately then doesn't matter what all the other numbers in this product are going to be, because if we're multiplying by 0, the result has got to be 0. So therefore, recalculating those two products we came across earlier, the first of which was this one, this is where we got up to before, but now we can therefore say, well, it's going to be the product of 4 from -6 to -1, times by the product of u from -6 to -1, and therefore that's individually going to be calculated in this way. The product of 4 is going to be, well, just 4 multiplied 6 times, because there's 6 terms between u equals -6 and u equals -1. And then using this new formula we derived for situations where the values we're plugging in are all negative, we have -1 to the power of 6 times by 6 factorial. And that will get us a final answer of 2,949,120. Nice. And then the other scenario we looked at was this particular product here, and we'd got to that point where the interval for v was from v equals -2 to 2. And therefore, without doing any more calculation, I already know the answer is just going to become 0, because one of the terms of the sequence will be 0. Okay, so what first started off appearing as if it would be something very simple turns out to be a bit of a weird thing when you're dealing with sequences of the form a lots of r plus b and trying to apply the product of those sequences. So if adding is now a pain to do with products, that doesn't bode well for if we're trying to do other operations. Adding is often one of the easiest things to do with most operations, so surely it's only going to get worse from here, right? Not quite, because actually if you're trying to find powers, those actually do work very nicely with products. Let's look at a quick example. Let's say we're doing the product from the first term to the fourth term of r squared. That, of course, is calculating 1 squared times 2 squared times 3 squared times 4 squared, and in turn, each of those squared things individually mean this. But because it doesn't matter what order you multiply things in, that commutative property we talked about earlier, we could rewrite this in this order. And the reason we might want to do that is now we've got 1 times 2 times 3 times 4 appearing in two places, which is individually the product of r from the first term to the fourth term, meaning we've just got that product all squared. Which therefore leads us to realize that actually, when it comes to powers being applied to a function and then finding the product of that function, then we can just apply the power after doing the product rather than the other way around. Super nice, super easy. But this leads to an interesting disparity between the difficulty of calculating series and calculating products. If you're calculating the series of 1 over r from r equals 1 to r equals 6, it's a bit weird, because if you want to know what that result is, officially it's called the sixth harmonic number. But as most calculators don't have a harmonic number function, and because there's no formula for just instantly calculating the series of 1 over r, you effectively have to calculate that manually if you want to find that result. Whereas if we're trying to find the product of this sequence, it's super easy, because 1 over r is just r to the power -1, and therefore we can just do the product from r equals 1 to r equals 6 of r, then take it all to the power -1 afterwards, which is just going to be 6 factorial to the power -1, which is just 1 over 720. Super easy to calculate with pretty much any scientific calculator. Pretty sweet. And at this point, you might start to feel like you're getting quite a good grip on how to both manipulate and calculate various products. However, I do have one more trick to show you today. A few moments ago, we were looking at products of sequences with an nth term of the format AR plus B, where A and B are constants, and we said they're a bit of a pain in the butt to deal with, because ultimately it was only when B was a multiple of A that we could do that trick that allowed us to factorize and then find a formula for them. However, I wasn't telling you the whole story there, because there is one more type of sequence that fits in this format of nth term that is still possible to find the formula for. And that is any sequence that involves finding consecutive odd numbers. So for instance, we're looking at an nth term of the format 2r minus 1, and you'll notice interestingly that this number is not a multiple of this number. Technically it's the other way around, but that's still a problem because that doesn't fit with what we were dealing with before. We're going to look at this sequence from r equals 1 to r equals 8 and of course find the product, and therefore that would be these numbers multiplied together. We could decide to stick with what we know and start trying to use factorials. For instance, if you work out 16 factorial, it would be these numbers, and the good news is that would at least include all the numbers we want to find the product of, but the problem is it's also including a whole bunch of numbers we don't want to find the product of. So we can correct that issue in theory by then dividing by those numbers to then only leave us with the numbers we care about. But that's a trick that's only helpful if the sequence we're dividing by is a sequence that we can easily find the product for. Good news though, because of the very specific scenario we're dealing with, the numbers that we're dividing by all happen to be the even numbers. So therefore they have an nth term of 2r. And that's great news because we already dealt with finding the product of sequences that are of the format a constant times by r. And therefore we can calculate this product. All we got to do is we got to do 16 factorial to deal with the stuff that's on the top, and the bottom would be just 2 to the power of 8 times by 8 factorial. And therefore, boosh, the answer is 2,027,025, and at this point we feel like a bit of a boss for pulling that one off. Wow, though the thing is, this is only the beginning, and we could look at way more sequences trying to find the products of those sequences. Like for instance, what happens if we want to find the product of a geometric sequence? Or what happens if we want to find the product of weird looking sequences like this? Is it possible? Is there going to be a formula for it? But I feel like I've kept you here long enough as it is already, and so therefore, please do subscribe, like the video, leave a comment, let me know if you'd like me to do another future video exploring this topic further, because there's still so much more I could talk about this stuff. And so hopefully you've enjoyed today's video. I've got on the screen right now some links to some of my other videos, like another video in the Can We Do That series, and another video in the Prove It series, and also the Can We Do That Some More companion video that I always release every Monday after the original Can We Do That video. I will see you in one of those other future videos. Goodbye!